Hey guys, this is Yoru. Today I'm going to introduce some basic knowledge we need to understand before we move on to the detail about CAD form mechanism. The first thing I'm going to talk about is the coordinate system. The definition of coordinate system is a system which uses one or more coordinates or we say variables to uniquely determine the position of a point. There are basically two types of coordinate system we use a lot in analyzing a mechanism. The first one is the generalized coordinate, which you may have already been familiar with. It consists of three coordinates, which are theta 1, 2, and 3. And also, since the system is a single degree of freedom system, we will need two constraint equations. But for generalized coordinates, we need other relationship to find positions of all rigid bodies. Therefore, it is not very convenient for us to design a general-purpose computer program. The second type of coordinate system is Cartesian coordinate, which we will use a lot in the following lectures. If we want to use this coordinate system to describe the motion of a four-bar linkage system, we will need 12 coordinates and 11 constraint equations. Don't worry if you don't know how to derive 11 constraint equations here. We will talk about that later. The reason why we need to learn Cartesian coordinate is that it has all the coordinates we want to analyze, and we can determine all these coordinates at once. And by the way, the constraint equations when using Cartesian coordinate can also be applied to dynamic analysis. That's why we usually use Cartesian coordinate when analyzing 2D mechanism. Here is the comparison between generalized coordinate and Cartesian coordinate. For the number of coordinates, there are more in Cartesian coordinate, but have fewer steps to calculate all positions and orientations. And it is also easier to develop a general-purpose computer program using Cartesian coordinate. The other basic knowledge we must know is the coordinate transformation. In Cartesian coordinate, we always give a body fixed coordinate or so-called local coordinate to each rigid body. And we also have a global coordinate which will be set on a fixed point. The relationship between the local coordinate and the global coordinate is called coordinate transformation. Once we know the coordinate transformation, we will be able to find the position of any point on a rigid body, just like the point P on the picture below. That's why coordinate transformation is very important. There are two types of transformation. One is translation and the other is rotation. So for example, if we know the position vector of P in local coordinates, we call it RPI, where the I represents the ith local coordinate. And if we also know the coordinate transformation between local and global coordinate, then we can determine the vector Rp, which is the position vector of P in global coordinates. Note that the vector RPI I mentioned here is the position vector of a fixed point P relative to the local coordinates. That means that point P's local coordinates will never change. In this case, its position will always be 1, 0 in the local coordinates. Okay, so for the coordinate translation, it is basically just a simple xy offset. As the example shown here, we can easily see that the relationship between local and global coordinates is Ri, which can be expressed as x offset by xc and y offset by yc. So if we say the position of P in the local coordinates is x local, y local, then the position vector of P in global coordinates, which is Rp, is xc, yc plus x local, y local. Easy, right? Then for the coordinate rotation, things will be a little bit complicated. Same, we want to find the relationship between local and global coordinates. Here, we can use trigonometry to help us. In local coordinates, we say P is at x local, y local, which is the black dashed line. If we express it with vector length L and angle alpha, we will get x local equals to L cosine alpha and y local equals to L sine alpha. But here we also know that the angle difference between local and global coordinates is theta. So we can use trigonometry again to find x global equals to L cosine alpha plus theta and y global equals to L sine alpha plus theta. And you will notice that we can substitute L cosine alpha and L sine alpha with x local and y local. Great! Now we get a relationship between local and global coordinates. If we write it down in matrix form, we can get something like this. And the matrix here, we have another name for it. It is called rotation matrix, since it describes the rotation transformation of a coordinate. So in general, to describe a coordinate transformation with both translation and rotation, we can combine the results we derived just now and get the equation in this form. Okay, that's pretty much all you need to know before we get into the detail about CAT. See you next time.